All right. Good morning, all. I hope you are enjoying your snow day. Maybe got to sleep in a little bit. These notes, hopefully, you were able to find on Canvas. I'll also attach it to the Skyward message with this PDF. So, should keep us on schedule and not let us fall behind anymore. What you're going to see here on this first page, for the most part, is what's called integration by parts as the section. But this top 2/3 of the paper is really just all of our antiderivatives that we've done throughout the course of the year written out. It fills in a couple of blanks. You're not necessarily responsible for these, but we've done the antiderivative of cosine. We've done the antiderivative of sine. We've done the antiderivative of tangent. We've done the antiderivative of cotangent. The one that we don't really do, you're not really responsible for it. The method that would get used to actually do it is not something that we would talk about, is the antiderivative of secant and cosecant. Again, you're not responsible for it, but it just kind of fills in the final types of antiderivatives and functions that we've dealt with this year. But the rest of these are really just the different types of antiderivatives that we have found. So as we move through this chapter and we revisit how to do antiderivatives, this page is a nice little reference to look at if we do get stumped along the way. Eventually, though, we do get down here to what you're going to see where it says integration by parts, and then that is the title of our section. You'll see here it says the integration by parts is, quote unquote, the product rule for integration. That implies that integration by parts is usually used when we have a product between multiple functions and U substitution wouldn't work. Like I mentioned yesterday, U substitution is still very much a viable option, so we don't want to skip over that. That's really kind of the second option. We only go to these new methods if U substitution doesn't work. Integration by parts typically is going to be when you have a product. So that's what this is indicating here. When you have two functions multiplied by each other, U substitution doesn't work. So if you try to integrate x cosine 2x, U substitution is not going to work. So then we obviously need a different method. It says the formula for integration by parts is derived from the product rule for derivatives. I'm just reading this sentence right here. What that implies is, so if you kind of look right here, let me explain where I would have gotten that from. This is really just when we would have learned the product rule a long time ago, the product rule for a derivative. We talked about how we leave, in this case, the first term alone, and then we did the derivative of v, and then the product rule you add, and then you do the opposite. You leave the second term alone, so we leave the v alone, and then we take the derivative of u. So it's just our product rule. Take the derivative of one, leave the other, and then add, and then interchange what we just did there. Take the derivative of the other one, and then leave that first term alone. What you're going to do with this now, the way this is derived to figure out our antiderivative now is, if you notice, all of these have a dx, all three terms that are now a part of this equation. So if we just said we multiply by dx, since they all have a common denominator, it would really just cancel all of these out. So that's why in this next step, since they're all being divided by a dx, that means all their numerators would have to be equivalent to each other. So that's where, again, this comes from. Then just did a little bit of algebra here. If you notice, I just solved for this right here. So that would require us to move this guy over. That's why the v du becomes negative in this second step. And then since we're solving for this, I just put this on the left-hand side. So this is, again, derivative of a product rearranged. So when we do integration by parts, we want it to look like this. And then when we do our substitutions that we're going to be doing here in a minute, our substitutions are going to be one for u and then the other for what we call dv. And then the integration of dv, if I did the integral of this, would have to be the integration of both of the right-hand side terms as well. What you want to notice is, I'll highlight it, when we take the derivative or antiderivative of these three terms that we created via the product rule, this one right here, notice how we're finding the antiderivative of a derivative. So this goes back to a couple chapters ago with that fundamental theorem, the idea that those cancel each other out. So that is why in that next step, this uv will end up standing alone, because it would end up right where we started. If we did the derivative first and then brought it right back with our antiderivative, we would just end up with whatever we started with. So that's why this just becomes our uv. This looks odd. But this is the formula for integration by parts. So it is the integral of u dv is equal to the product of u and v minus the integral of v times du. All right, looks odd. Probably don't expect you really right now to kind of understand what exactly all those variables mean. But what I do want you to kind of just understand and recall is, there we go, that it's really just our product rule for derivatives, and we're doing the antiderivative of that result. Should bring us back to that original idea. So let's go to the next page. Here's our formula again. U dv minus uv minus the integration of v du. We'll kind of walk through these steps here as we do number one, especially now that I want this, you won't be able to see the problem and these steps. So if you look at number one, step number one tells you to find the integration of u dv by substituting one of the functions as u and the other function as dv. So what that means is when we go to number one, we want to identify this as a product. So again, integration by parts is considered kind of the product rule for antiderivatives. We have two functions. We have the function x, we have the function sine of x. So what I'm saying up here, since we have two different functions, one of those functions is going to be your u, and then the other function you're going to say is part of your dv. So when we come down here, what I'm going to do off to the side, I'm going to let u equal, in this case, x. And then what I want you to do, kind of kitty corner to this, so kind of at a diagonal, write in dv. So if u is going to be the x, the other function that we have in this problem is the sine of x. So we're going to assign sine of x to dv. And then notice this is our change in v, our dv, derivative of v, all those words we can use. That's always going to also account for the dx. So we're going to let dv equal the sine of dx. So we have all parts of this guy right here accounted for with a u and a dv. All right. So what we're trying to do is find the antiderivative of x times sine of x and then our dx. So our formula is u times v. Well, we have a u right now. We don't have a v. And then you're going to have to do minus the integration of v times du. We have hold on here. Yeah, we have our, we don't have either one of these guys. So we're going to figure these out. Hold on, I got confused myself for a second. I was looking for the v and the du. We need to find both of these guys. Okay, so here's how this one is now going to get set up. U, we said u is going to be an x. Well, the v we don't have, but I could create a v if I come over here and do the antiderivative. These pens are a little sketchy these last few days, of dv. So if I did the antiderivative of dv, that gives me a regular old v. It's like a 1 right here. So then the antiderivative of 1 dv would just give us a v. And then the antiderivative then of that right-hand side, what it would be equivalent to is a negative cosine of x. So if our formula is u times v, then what I am now doing is taking this u, which was x, multiplying it by the v, which we just found to be a negative cosine of x. Then I'm going to subtract. Then we now want the integration or antiderivative of v multiplied by du. We now know our v, that's this negative cosine of x. We don't have a du, but if we come over to our u equation, can't I take the derivative of this? So initially we would say du dx is a 1, but like we did with u substitution, we just multiply that dx over. So what du really is equivalent to is a dx. So the du gets multiplied by our v. This is our v. The du in this case is just becoming a dx. If we now want the antiderivative of x sine of x dx, we just finish off the right-hand side. So this, simplified, would just give you a negative x cosine of x. And then here, notice how we have minus a negative. So there's different ways we can handle it. You could do your antiderivative first. I am actually going to go ahead and say this is really a positive overall, so that this cosine is considered positive. So the antiderivative of a positive cosine then is sine of x, and then plus your constant. I won't do it for all of them, but just to show that this method does work, I should now be able to take the derivative of this and end up again right back with what we started with. So let's go ahead and do that. I'll kind of show how this works. So now this is our product rule. First term, second term. The derivative of the first term is a -1, and then we leave cosine. Product rule, you add, leave the negative x alone. The derivative of cosine is a negative sine of x, plus the derivative of sine of x is cosine of x, and then the derivative of any constant is going to be a 0. So what you'll notice, we have a negative cosine here, we have a positive cosine here, so those are going to cancel. In here we have negative, negative, creates a positive overall product of x sine of x. The constant drops out. Notice how this was, in fact, what we started with. All right. So that's integration by parts. The key is this. When I said we need to define our u and our dv, we need to define this, and then we need to define this. One of them, then you're then going to go up with an antiderivative. The other one, you're coming down with a derivative, and then we just enter it into our formula. All right. All right. So number 2. In order for this antiderivative, x cosine of x dx, again, here's our general formula, u times v minus the integration of v du. Up here, I'm going to let my u equal x. I'm going to let the dv equal cosine of x. And then always the dx would go into that spot as well with the dv. So the u is this first term, and then dv takes care of everything else. We have everything accounted for in our formula. Again, what we need is a u. We have that right here, but we also need a v. We don't have that, but what we showed on the previous one is in order to get v, I would want the antiderivative of dv, this 1 dv. So the antiderivative of 1 times our change in v would be just the variable v. Antiderivative of cosine is sine. We now have this v, we now have this v. What we're still missing is this du right here. The way we get the du is by taking the derivative of whatever we identified as u with our original substitution. So du then is a 1, and then dx. All right, so now we do our substitutions. X cosine of x dx, this is what we want the antiderivative of, is equal to the product of u and v. So here is u, here is v, that is x sine of x. Then you're going to have your minus sign, and then we still want to find the antiderivative of v multiplied by du. So it's these guys here. Here is the v and the du. So that's really just sine of x dx. Final answer then. The antiderivative of x cosine of x dx is this x sine of x. And then, again, treat this how you want. I'm going to treat this as a negative sign, and the antiderivative of a negative sign is positive cosine of x, and then plus your constant. If you wanted, go ahead and take that derivative. Promise you're going to end up getting what we started with there, that x cosine of x. All right, 3. When we come down here, picking our u and our dv, you may be wondering now, how do we know what we're picking? So actually, on that note, let's actually jump to 4. So go to 4. Just kind of had a thought that maybe this would be a better one to do right now. So go to 4, and let's pick our u and our dv. And what we want is the antiderivative of x squared e to the x should equal, again, u times v minus the integral of v du. So I'm going to write that out the first few times so we get that thing memorized. Make sure I got enough room here. All right, so here's the general rule for doing these. So when we come up, no, you know what? I don't want to tell you general rule yet. Let's go to number 4. What we're going to let our u equal is x squared. And then our dv is going to be e to the x and then the dx. All right, hopefully at this point now we see, after doing a couple, that we're going to need the derivative of the u, which would be 2x and then dx. And then we need the antiderivative of the dv, and the antiderivative of e to the x would just be itself. From there, we go ahead and plug it in, x squared e to the x. U, v is these guys here multiplied together, x squared e to the x. And then minus the integration of v du. V is e to the x, du is 2x. I'm going to write that as 2x e to the x, and then your dx. Our answer now should be, when we go to do this, and it's worked for those first two that we did, numbers 1 and 2, where this guy's ready to go. It's just x squared e to the x. And then minus whatever we get for this. However, hopefully we recognize right now we still have a problem over here. This is still a product between 2x and e to the x. And we can't just do the antiderivative of each term when it's a product of those terms. So what we would hopefully see, and usually there's kind of this collective groan in class when we see this, is this idea that we basically have to do another u substitution problem for this guy right here. So off to the side, we've already used these substitutions for the original problem. Now we need to come up with another set of substitutions for the problem that resulted from the original problem. All right. So one rule we want to make sure we understand when we go to do our u, when we do these repeated ones, so this is not necessarily uncommon where we have to do this multiple times. If you let u be the x squared term and we let the dv be the e to the x, we need to make sure we keep that relationship the same. So we now definitely want our u to be the 2x, and then our dv would be the e to the x and then the dx. Just like the other ones, we want the derivative of u, so that's 2dx. And then the antiderivative of dv would again give us an e to the x. When we now go to set this up, be really careful, because what I have highlighted in blue is going to create one of these guys. It's going to create a binomial, and we have this negative hanging out in front. So that negative is going to need to get distributed to this binomial that we're going to create with our formula here. So using these substitutions now, I'm going to take the u and the v. So here's u, here is v. So that's going to be 2x e to the x minus the integration of v du. So again, v times du. V is e to the x. Du is 2dx. I'm going to write that as 2 e to the x and then dx, and then I'm going to close that bracket off. That's how we kind of make sure that this negative is going to get distributed to both terms. So now what's going to happen is you cross your fingers here that we're done, and we don't have to do this again. And the way we will know we are done now, this is going to be fine now. This is a negative 2x e to the x. This should ultimately become a plus, this negative multiplied by that negative. And then you just hope this has a nice, easy antiderivative that doesn't require us to do another one of these substitutions here. Hopefully we see that, and it does. That the 2 we drop down, and then the antiderivative of e to the x is itself. And then add your constant, and then that's going to be our answer. Sometimes in class, I actually do this one. I won't, since you're on video. Don't want to bore you too much. Doesn't look like the derivative of this would end up giving you this, but if you want to pause and have a little fun with that, you just have some product rules, and as long as you do the product rule here correctly and here correctly, along with this derivative, when you go ahead and simplify everything, you do still end up with that just simple little x squared times e to the x term, which is kind of cool, I think. All right, so now back to what I kind of was starting to say before. How am I getting my u's? Like, where are we getting them from? So the general rule for your u, and we can now see it in number 4. That's kind of why I waited. Now that we see we could do this multiple times, we not only did it this initial time, but we had to do it another time right here. You can see that sometimes you may have to do this repeatedly. You have to do it a few times. So as a general rule, in order for this to eventually give us something nice like it did here, what you're going to want to pick for your u is whichever one of these functions, if we have one, the derivative would eventually terminate. So what I mean by that, if I did the derivative of x squared, I would get 2x, and then the derivative of 2x would be 2, and then eventually it would go away. If I did e to the x, it would never go away. All it's going to ever do is continue to produce e to the x after e to the x after an e to the x. So when you have that decision to make, one of our general rules is that we probably want it to be the one that's going to terminate, and that would have been x squared in this case. Same up here. X derivative would have been a 1, and then the derivative of 1 would have given you a 0. It's done. Whereas if I did the cosine, if I start taking the derivative of cosine, I'm just going to go between positive and negative sines and cosines forever and ever. It's never going to terminate. All right. So that's our general rule when we have a basic function that terminates a derivative and the other one doesn't. So now, having talked about that, we're going to do one where that isn't the case. All right, so if we look at number 3, if I ask you to identify sort of what is the u, what is the dv, you don't really have any choice with this one, because what I mentioned earlier in problem number 1, the dv must always take care of the dx. They're equivalent ideas. They're both derivative ideas. So if we understand the dv has to take care of dx, the only thing remaining to be your u is this natural log. I should also mention we've done the derivative of a natural log. We haven't done the antiderivative of a natural log. That's why it's been waiting until this section, because the method that we need to use to find it is integration by parts. This, for sure, once we kind of see what it is, you're going to want to get it memorized. This you're now going to see routinely throughout the remainder of the year. So once we kind of figure out what this is, you're going to want to get it memorized. So our u is ln of x, dv is dx. We now hopefully know that we want the derivative of the u, and that would be 1 over x times dx. We want the antiderivative of these guys. So the antiderivative of dv would give you v. That would then mean the antiderivative of dx would just give you x. When we go to set this up, we would say the antiderivative of natural log of x is equal to uv, so that's x ln of x. And then we know we've got to subtract the integration of v du. So here is the v and the du. So notice how I'm going to be taking the x and I'm going to be multiplying it by 1 over x dx. So then you're all pretty bright people. We would understand then that when we multiply those together, those are going to cancel. So this is good. We know the antiderivative of this. This next step should be our answer. So moving forward, again, you're going to want to get this memorized. This one for sure. I promise you're going to want to get this down. The antiderivative of ln of x is this x ln of x here, minus, and then all we really ended up with is a 1 dx, the antiderivative of 1 being x, and then plus your constant. So antiderivative of ln of x is x ln of x minus x, and then plus c. All right. So a couple general rules. The first one being that whatever part of the function has a derivative that it will eventually go away, that's going to, more times than not, be your u. Another general rule, the dv must always account for the dx. All right, so definitely walk away with those ideas in mind. All right, when we go to this next one, number 5, when we do u, and then we do v, think about the rules that we just talked about here a moment ago, where we have 2 different functions, and we were looking to see which one's derivative would go away. Well, if you were paying attention here 5 minutes ago, we talked about how the derivative of e to the x would never go away. The derivative of cosine of x would never go away. They just continue to go on and on and on and on. When that is the case, you kind of need to make a decision, okay, in terms of which one that we want this to be. All right, so the one that I'm going to pick, I'm going to let u be e to the x, and I'm going to let dv be cosine of x, and then obviously we have to include the dx. When this is the case, when neither one of them terminates as a derivative, it doesn't matter which one you pick. You could pick either, but this is the one that I'm going to pick. So my du then is going to be e to the x, and then my v, when I do the antiderivative of this, would give me sine of x. All right, so then we're going to go ahead and set it up. E to the x cosine of x's antiderivative should equal uv, so e to the x sine of x, minus the integral of v du dx here. Then what you would hopefully notice, it happened back in number 4. When we look at this function right here, we still have a product. So this initial substitution got us this far, but then this one that I have highlighted in blue now, we would need an additional substitution for this guy. So if we go to that next step, you would get e to the cosine of x dx equals e to the x sine of x minus, and then again, be really, really careful with your signs here. This is going to create its own binomial, so I'm going to use brackets here, and then I have to do a new substitution for this one. If I let the u be the e to the x in this original one, then I need to make sure that u is the e to the x in the second one. And then that means my dv is sine of x, and then the dx. Derivative of the u is e to the x dx. My dog is introducing himself to you. The antiderivative of sine is a negative cosine of x. Use those for the new one. So u and v here give you a negative e to the x cosine of x minus, oh no, I hope I can squeeze this in, minus the integration of v du. So then that is these guys. All right, another negative e to the x cosine of x, and then our dx. And then I'm going to close this off. Go ahead and clean that up a little bit. Antiderivative of e to the x times cosine of x dx would now be, this guy was ready to go, so we just recopy that one. Go ahead and distribute here. So now this is a plus e to the x cosine of x. Careful with all of these signs over here. This initially gives us a plus, but we're distributing that negative to it. So we would get a minus. The integral is still there, e to the x cosine of x, and then dx. All right. Then again, what we're hoping for is we can look at this one here, and sorry, I'm trying to erase this. There we go. We can look at this one here, and then we're hoping that we can find the antiderivative of this. But when you look at this, usually I would ask, can we do the antiderivative of that right now, just right away, like we have been in every other one? Everybody realizes hopefully that you cannot. And what your first thought might be is, actually, there's two things you could think of. Some of us would be thinking, oh no, I got to do this again with these two guys. That's somewhat true. There's another group that's saying, yeah, I could do it again, but would it ever end? And the answer to that is no. That would go on forever and ever and ever. That's why, as a general rule, when we revisit these first couple, to make sure that eventually we will get to a nice final version, we want to pick the u that has, or make our u the function that has a derivative that will eventually go away. And our issue with this one is neither one of these functions' derivatives are going to go away. So normally, people wonder, how are we going to do this? And then I usually tell you that we're actually very close to answering this question right now. And then I ask if anybody is feeling clever, who wants to show off how clever they are with this, because at this step here, we're kind of ready to answer this question. So if you wanted to pause me and see if you could figure out something clever to do, go ahead if you're not seeing it. But I'm going to jump right in. And if I'm on 1.5 right now, or 2 times, then you could see this very quickly. But what we should notice is when we look at this guy right here that we created through these substitutions, isn't that the same as what we are trying to solve for? Notice how this is an equation right here. So with this being a minus, the exact same thing that we started for, couldn't I just add this thing to the other side, creating 2 of these integrals of e to the x cosine of x dx? On the right-hand side, all that would leave me are these 2 terms, the e to the x sine of x plus e to the x cosine of x. And then if ultimately my goal was to solve for what I have highlighted right here, here is what I have highlighted that I'm trying to isolate. That's the answer to the question. So can't I now isolate that with a quick little algebra step of dividing everything by 2? So I would now divide the left-hand side by 2 to get rid of the 2. And then that would take the other side and have a 2 in our denominator. Tack on your constant, and then that's going to be your answer. All right. So those are fun. Those are ones that make you think a little bit, but that's what you need to do typically if neither one of those functions are going to have a derivative that would go away. All right. All right, so that's integration by parts. There is also something that is equivalent to integration by parts that for most people, they consider this easier. And it's called tabular integration. So we did this problem already, right? So this antiderivative of x squared e to the x, this was problem number 4. This was our answer. So kind of keep that in mind, because tabular integration is an alternative. It's like a shortcut almost for integration by parts. So same exact problem. Here's what we got. So here's what tabular integration is. Tabular implies the idea of a table. So while we don't actually draw in like a table like this, kind of an XY table, that's essentially kind of what this is dealing with. So what you're going to do when we look at this problem, whatever you would have picked for your u. So when we look at this, we would hopefully understand now that u would have been x squared. That's going to be the left-hand side of our tables, the left-hand column. And you're going to take whatever that was, x squared, and we're going to actually go through all their derivatives until it zeroes out. So x squared, 2x, 2, and then 0. The other side of the table, we're going to take the other part of our function, the one that doesn't have a derivative that terminates, and we're going to do e to the x, e to the x, e to the x, e to the x. And we're going to do them. Notice how the x squared, and then as we took their derivatives to get to 0, there were 4 steps. That's why over here, I need 4 antiderivatives of the other function. Then what we're going to do is you can see these arrows here. The first actual u term, x squared, is going to get paired up diagonally with the first antiderivative. So when I do that, I'm going to do x squared times e to the x, and then notice how there's a plus sign here. So this first product, because there's a plus sign, basically just means you're going to keep whatever sign would have occurred naturally between x squared and e to the x. Then what you're going to do is take this 2x, and we're going to multiply it by the next antiderivative, and notice how there's a minus sign right here. So 2x times e to the x would normally be just 2x e to the x. It's positive. But because there's that negative sign right there, we're going to switch that sign. We go to the next row. You're now going to do, I don't want to do that. You're going to do the 2, the third term in the derivatives, multiply it by the next antiderivative. That would be 2e to the x normally. And then since this third sign is a positive sign, that just means you're going to keep whatever sign would have occurred naturally between this 2 and e to the x, which would have been positive. So this is positive. We don't have anywhere else to go because you have zeros afterwards. So that means you're done. And then you do your plus c. This is the same exact answer that we got when we did it with integration by parts. All right. So you can kind of look at this one here. If we don't do tabular integration right now, so hopefully we're understanding a little bit to understand that if I did u here, I would make my u x cubed. Now that this is an x cubed, if we went through all these derivatives, you would actually now need to do, like here, you thought you had it bad in number 4, where there was an x squared here, you would have had to have done this once and then twice. If this would have been a power of 3, you would have had to do a third substitution. So kind of ugly. So those higher order ones, this tabular integration is really nice. Because with this power of 3, you would have had to do 3 integration by parts. So tabular is nice. So what you're going to do is, since we know that's our u, you start with that, and then you just take all these derivatives until you get your 0. Whatever you picked for your dv, you start with that, and then you just do as many antiderivatives as we need. So since there were over here 5 layers to the derivatives, that means we would need an equivalent 5 antiderivative values over here. When you look at your signs always 100% of the time will start positive, negative, positive, negative. We continue to alternate. The answer then, look at where the answer came from. So now let me erase all of these so I can kind of show you where these all now come from. Is this first product x squared times a negative cosine of x. And the positive just means whatever sign would have occurred naturally between x cubed and a negative cosine, which would have been a negative. Since it's a positive, that just means a positive and negative would remain negative. So that's why this first term is a negative x cubed cosine of x. And then the next one, the next product would have been 3x and negative sine of x. So these guys would have normally have been a negative 3x squared sine of x. But since the second sign in our table is going to be negative, that's going to turn this into a positive 3x squared. So that is why down here, you're going to see this written as a positive 3x squared sine of x. If we do the next product, 6x cosine of x, and then you're going to keep that sign. So that just keeps everything positive. Last one, the 6 and the sign would have been positive because these are both positive coefficients or numbers. But since we're going to put that negative right there, we want the opposite, which makes this a negative 6 sine of x. And then that's our answer. Okay, so real quick, let's do number 7, because number 7 would take some time. So if I ask you to do number 7, what we want is the derivative of whatever you would have identified as your u. So that would have been x cubed. And then you just hammer out as many derivatives as we need to get to a 0. On the other side, you're going to do the antiderivative of whatever your dv would have been, and that would have been the e to the x and the dx. So here's our e to the x. We start cruising along with all of those until we reach the same spot as that 0. Our signs always start with that first row as positive, and then we just start to alternate. All right. We're ready to answer this question. So the answer to this question, this first product would have been x cubed e to the x, and since it's a positive sign here, then it just remains x cubed e to the x. The next product would have been 3x squared e to the x, which are both positive. But since the second sign, this is meaning we want the opposite sign of whatever these would have given us normally. So in this case, that means a negative. And then the 6x and the 3x is our third product. Our third sign is a positive, so we're going to keep those positive. And then our final one, our sixth product, would be 6e to the x. But it should be negative because of that negative sign. Tack on your constant, and then this is your answer. All right. So I guess we're recording, so you could stop me at this point if you're feeling confident with all of this. If you want to watch number 6, we'll do number 6 with just the sign. We want the derivative of u. We want the antiderivative of our dv. So our u would have been x squared. So we just take those derivatives till we hit 0. Our dv would have been sine of x. Do those antiderivatives, so negative cosine of x, negative sine of x, and then cosine of x until we reach the same line as the 0 is. Our signs are always positive, negative, positive, negative. So our first product should be a negative 2 or negative x squared cosine of x. Our next product, well, let me draw the line first, would be right here. So this would have been a negative 2x sine of x, but since the second sign is also a negative sign, that means we actually want this to be a positive 2x sine of x. And then lastly, this third product right here would be normally a 2 cosine of x. And then since we have a plus sign right there, that means we just keep that normal sign, tack on your C, and then that is your answer. Before you go, the tabular is usually what people really like. People like the tabular a lot. It's short, it's sweet, you get kind of a rhythm. It's the same thing over and over again. Where you need to be careful with the table. So here's the two instances where the table becomes really, really hard. So don't think the table now completely replaces integration by parts and you'll never have to do these UVs and DUs and DVs anymore. The table is not going to work for something like this because your derivative side would never stop. You would just continue to do e to the x's forever and ever. You don't know when to stop here. So the table won't work for that. And then the other place where the table won't work, or it's a lot harder, is when you're dealing with a natural log of x for a similar reason. So let me show you here if I can get the eraser to work. Think about what would happen if we did the table, the tabular integration, with this problem here. Our issue would have been if we want the derivative of u and then the antiderivative of basically a 1, ln of x was your u. The derivative is 1 over x. If I took another derivative, think of kind of our power rule, that would give us a negative 1 over x squared. Our same issue happens with a natural log. These never go away. All right. So when there's a natural log involved, when neither one of them has a derivative that terminates, you still want to know your integration by parts really well. There's other ways to kind of test you on that also. But in all honesty, most people, for most problems, really like the tabular because it's pretty short and sweet, and that's what most people kind of go with. So it's up to you. There is a quiz review online as well. I'll talk about that tomorrow. I'm going to see all of you guys tomorrow. The quiz on this will be Tuesday of next week. You have that quiz review, and then you can try some, see if you can do them on your own. The quiz is pretty quick. It's just the second half of the class period. So hopefully this made some sense. I'm sure I'll see all of you guys tomorrow if you did have any questions. But enjoy your snow day. We'll see you tomorrow.